All right, let's talk about two of the most essential and maybe a little bit secret tools that every programmer has in their back pocket: stacks and queues. Now, they might sound kind of basic, but they are incredibly powerful, and really understanding them is the key to solving some seriously interesting problems.
Okay, so to get us started, let's just jump right in with a puzzle. Take a look at this string of brackets. Now, you and I, we can probably trace it with our finger and figure out if it's all matched up. But how on earth would you teach a computer to do that? Especially if this string was, a million characters long.
This little problem is famously known as the valid parentheses puzzle. It's a classic for a reason, and while it looks like just a simple matching game, trying to solve it efficiently can get surprisingly messy if you don't have the right tool for the job.
So what we really need here is a system, a structure, that just inherently understands this kind of last one opened must be the first one closed logic. And that, my friends, brings us to the hero of our story today. Meet the stack. It is literally the perfect data structure for this puzzle, and its core principle is the entire secret to cracking this thing wide open. So what even is a stack? Well, it's super simple. It works on a principle called last in, first out, or LIFO, as you'll hear it called. The absolute best analogy is a stack of plates. The last plate you put on top is the very first one you have to take off. Simple, right? And it only really has two main jobs. Push is when you add an item or a plate to the top. Pop is when you take that top item right off. That's it. Push and pop. Remember those two.
All right, we've got our puzzle and we've got our tool. So let's walk through the solution step by step and see just how this LIFO principle turns a tricky problem into something, well, almost trivial.
We're going to start reading the string character by character. And the rule is dead simple. Anytime we see an opening bracket, we push it onto our stack. First up, this curly brace. Bam! On it goes. The stack is now holding on to it for us. We move to the next character, an opening square bracket. The rule's the same, so we push it right on top of the curly brace. You see what's happening here. The stack is basically acting as our short-term memory, keeping track of all the brackets that are open and are now waiting for their match.
Okay, and here is where the magic really happens. We've hit our first closing bracket. Now the rule changes. We take a quick peek at the very top of our stack. Hey, is that the matching opener? In this case, yes. The square bracket on top is the perfect match. So we pop it off the stack, they're a pair, they're resolved, gone.
And that's really the elegant rhythm of the whole solution. You see an opener? Push it on. You see a closer? Check the top for a match, and if you find one, pop it off. We just repeat this simple dance of push and pop all the way through the string.
So we follow this pattern all the way to the end. With each matched pair we find, our stack shrinks, cleaning up the open tasks we had stored. It's almost like we're tightening up as we go along.
And here's the grand finale. We have reached the end of the string, and our stack is completely empty. That is our signal. That's how we know for certain that every single bracket was perfectly matched. Success!
And what's wild is that this LIFO logic isn't just for brackets. The very same principle can solve totally different problems, like, say, simulating asteroid collisions. I mean, think about it. The last asteroid you see is the first one that has to confront the next one coming along. It's a direct matchup handled by the top element of the stack. Different story, same exact tool. But what if you need things to be fair? What if the first one in line should always be the first one served? Well, for that, we need a different kind of tool. So let's move on to the stack's cousin, the queue. A queue is pretty much the philosophical opposite of a stack. It follows the first in, first out, or FIFO principle. So while a stack cares about what's most recent, a queue cares about who's been waiting the longest. The perfect real-world example is a checkout line at a store. First in, first out. And instead of push and pop, queues have NQ and DQ. You NQ to add someone to the back of the line, and you DQ to serve the person who's been patiently waiting at the very front. It is all about fairness and order. So why does all this matter? Well, stacks literally power the undo button in your editor. Every action you take is pushed on, and when you hit undo, it just pops the last one right off. But queues manage fairness. Think of your printer. You send 5 documents to print. It uses a queue to make sure they print in the order you actually sent them. Your computer's CPU does the same thing, lining up tasks so the first one requested gets the first slice of attention. So we have these two simple yet really powerful tools that operate on completely opposite principles. And the key to elegant problem solving is simply knowing which one to pick for the job at hand. Let's just break it all down one more time. A stack is LIFO, last in, first out. It uses push and pop. It's your go-to for problems that need reversal or matching up pairs, like our parentheses puzzle. A queue is FIFO, first in, first out. It uses NQ and DQ. It's absolutely perfect for processing items in the exact order they arrived, like a print queue or a support ticket system.
Ultimately, choosing the right data structure, it really is like a programmer's superpower. It's what allows you to take something that looks complicated and chaotic and find a solution that's simple, elegant, and just works. So now that you get the fundamental logic, last in, first out versus first in, first out, start thinking about it. What other everyday problems or even complex puzzles could be solved with something as simple as a stack of plates or a line at the store?